Hi, I'm Joel, and this is Live Coding Madness. Let's build a deep learning library. So, who am I? I am a research engineer at the Allen Institute for Artificial Intelligence in Seattle. I wrote a book called Data Science from Scratch. It's good. You should check it out. I have a Twitter account. It's also good. You should also check it out. And I am the co-host of a podcast called Adversarial Learning. Please listen to it. I think you'll like it. So today we're going to be live coding, and I live code the way that I live code, which is to say I use type hints on everything. So if you're not used to type hints, get used to them because I'm using them. I use Python 3.6. I use Python 3.6 only features. So if you don't use Python 3.6, get used to it as well. I'm going to type very fast. That's how I type. I'm going to talk very fast too. It's possible I'll swear at my text editor. Sometimes it does autocomplete in a bad way that makes me really angry. And we are going to be building a deep learning library. So not just some code that does deep learning, but we're also going to be doing making a library that's extensible, that can solve lots of different kinds of problems. To that end, we're going to use good abstractions. We're going to use good variable names. We're going to document what we're doing. And we're going to make heavy use of MyPy, which is a Python static type checker, and Pylint, which checks for style. And they will hopefully find all of our mistakes before we ever run our code and allow us to code very quickly. And if this were live, I would say you tell me when I screw up. This is not live. It's recorded, so you can't do that. You can still tell the screen and pretend like I hear you, and hopefully I will fix the things that you see. So we're going to build a deep learning library. We should probably talk about what deep learning is. Here's a one-slide version of it. We represent our input data as multidimensional arrays. You know, an image might be have a width and a height and a number of channels and an intensity for each of those. And then we'll predict outputs using a parameterized deep neural network. We'll have a loss function that depends smoothly on the parameters and tells us how good our predictions are. And then we'll use some combination of calculus, greediness, and cleverness to find parameters that minimize loss and that therefore result in good predictions. And so I have a plan. It's an outline I'm going to use because without it I can't get this done. Tensors, we'll do loss functions, we'll do layers, we'll do neural nets, we'll do optimizers, data training, and two end-to-end examples, XOR and Fizzbuzz. So now it's time for some live coding madness. So I made this directory called JoelNet. I'm going to call it JoelNet because that's me, Joel. And right now it has a README and nothing else. It also has, git ignore and a Pylint RC. And it's got our plan in it because I need this plan as a cheat sheet. And what I will do is I will make a directory called JoelNet to put our library in. And because it's a Python library, I need to add an init.py to that folder. And finally, I will start a VS Code window here and use that as our editor. So it's got the README, and that's got our plan, which is perfect. So we made this JoelNet directory, and the first step in our plan is tensors. So let's add a file. I'll call it tensor.py, and we're going to use doc strings and everything to document everything. A tensor is just an dimensional array. And if we had a lot of time, we would create like a really good full-featured tensor class. We don't have a lot of time and we're in a hurry, so I'm going to cheat and say from numpy import ind array, which is the numpy in-dimensional array class, as a tensor. And we're done. That's our tensor class. We can move on to the next best thing, which is loss functions. So let's add file to have loss functions in it and get rid of this explorer. We'll say a loss function measures how good our predictions are. We can use this to adjust the parameters of our network. So what does a loss function look like? Start with let's import from JoelNet.tensor. Let's import the tensor class. And I happen to know I'm going to need numpy, so I'll import numpy as np. This is traditional. So our loss function will have two methods on it. One I'll just call loss, and it will take some predictions, which are going to be a tensor, and some actual values, which will also be a tensor. And it's just going to return a float. So some number, and this is our abstract base loss class. We'll be able to implement a lot of different losses. So we'll just raise not implemented error so that if someone tries to use this base class, it won't work. And now we also have a grad function. So this grad will be the gradient, which is the vector or matrix of partial derivatives of the loss function with respect to each of the predicted things going into it. So it will also take predicted as a tensor and actual as a tensor. And this time it itself will return a tensor, and it will be the same shape as predicted because it's just the vector of partial or the tensor of partial derivatives of the loss with respect to each of those predictions. And again, this is the base class, so let's raise and not implement an error. And now we want to implement an actual loss function. And so let's call this MSE for loss. MSE is mean squared error, although we're just going to do total squared error. So I didn't name it right, but I like calling things MSE, so don't tell anyone. So how do we do the loss? Well, we want to do total squared error. So the error is just predicted minus actual, and then the squared error will square it. And then if we want to take the total, I'll just do np.sum. And so I sum up the predicted minus the actual squared. And for the gradient, you know, when you have a function squared, its derivative is just 2 times x, and it turns out that that's the same thing here. And so the gradient of this function is just 2 times predicted minus actual. And we've set this up so that we could implement a lot more different loss functions. But for today, we're only going to implement these two, and I should probably put return because otherwise it won't work. And that's all we need to do about loss functions. So now our next step, part 3, is layers. So let's add layers.py. And so what are layers? Our neural nets will be made up of layers. Each layer needs to pass its inputs forward and propagate gradients backward. And we'll talk a little bit more about that when we implement it. For example, a neural net might look like, so we have some inputs, and we send them through a linear layer, and then we send them through a hyperbolic tangent activation layer, we send them through another linear layer, and those are our outputs. And so here's where we're going to build the layer machinery to make that happen. So from joelnet.tensor, we're going to need the tensor class, and we're probably also going to need numpy again. Import numpy as np. And I think that's good to get us started. So let's define a class for a layer. And I am going to give it a constructor because I happen to know that I want a constructor, but it's not going to do anything for right now. And it's going to have 2 methods. One I'll call forward, which will take some inputs, which is a tensor, and will return a tensor. And you know, I'll call it produce the outputs corresponding to these inputs. And since this is the base class, I'll raise the not implemented error. And then it's also going to have backwards, which is going to take self and some gradient, which is a tensor. And again, it will return a tensor, and it will back propagate this gradient through the layer. So if we have a gradient, which is the partial derivatives of some function, which in practice will be our loss function, with respect to the outputs of this layer, backwards will take it and it will produce the gradient of that same function with respect to the inputs of this layer. And then along the way, it will also save the gradients with respect to the weights, and you'll see that in a second. But so we'll raise a not implemented error here too, and that's our layer. So now I haven't done this, but let's run MyPy. So MyPy is the command line static type checker. I'll run it on JoelNet, and I need to add this flag, ignore missing imports, because we're using NumPy, and NumPy does not itself have typeint. So if I don't use that flag, it'll throw me a bunch of errors and warnings that NumPy does not have all these typeints. I'm not going to write typeints for NumPy today. So MyPy is happy. So far, we haven't made any egregious type errors. So now our first layer is going to be a linear layer. And so what is a linear layer? A linear layer just computes output equals inputs matrix multiplied by some weight. That add is the matrix multiplied in Python 3.6 plus some bias term. And so that's all this layer does. It's linear regression or linear function or whatever. So it will need a constructor, and in particular, we need to tell it an input size, which is an int, and an output size, which is also an int, and returns none. Incidentally, these are the type ints I've been talking about here. We say this input size needs to be an int, this output size needs to be an int, and MyPy will insist that all of our constructors return none. And this way, when we check, if at some point we try and feed in something that's, say, a string here or whatever, a tensor, it will, actually with tensor it might not get angry for various reasons, but if you try and give it a string, it will get angry. So what do I want to do? Well, I'm going to use this input size and output size to create the parameters. So this, I have this weight parameter, which is what I want to multiply our inputs by. And I'll just add a comment here. Inputs will be batch size by input size, and outputs will be batch size by output size. We're going to do all of our layers to take batches. So we have we want to multiply batch size input size to something and get batch size output size. So that's going to be numpy dot, and I'll just initialize it with a standard random normal, which is input size by output size. And then similarly, I need self.params.b to be np.random.randin, and just if I do output size, it will broadcast correctly and we'll be fine. So if I go now and do MyPy again, it's probably going to complain, and it will complain linear has no attribute params, right? So I tried to assign to this dictionary, but that dictionary is not defined in the base class. So self.params is an empty dict, and now I need to make sure to call the superclass constructor to get that dict initialized. And now, if I do this, it's probably going to complain again. Need type annotation for a variable. All right, so layers.py16. I've defined this self.params. I didn't tell it what type it is, so I can't do anything with it. So this is going to be a dictionary whose keys are strings and whose values are tensors. And now this dict is not built into Python. So from typing, which is where a lot of type int stuff comes from, we have to import dict. So now we say these params are a dictionary. And now I think it will pass. Okay, good. So now here we get to the interesting part, which is, pushing inputs forward through this linear layer. So we have some inputs which are a tensor, and we want to return a tensor. And again, let's just repeat: outputs equals inputs at w plus b. So the only really interesting here is that we want to save a copy of the inputs, which I'll say self.inputs equals inputs, and that way when we do the backpropagation, we can use them because we're going to need them. And then all I want to do is inputs at self.params w plus self.params b. So that's all the forward has to do. It's nothing exciting. It's nothing that interesting, although maybe it is interesting. So the backpropagation is where something really interesting happens. So I have some gradient, again, which is with respect, the gradient of some function with respect to the outputs of this linear layer. And I want to backpropagate it to get the gradients of that function with respect to the inputs of this linear layer. And then along the way, I also want to compute the gradients of that function with respect to the parameters within this layer. And so you'll see what I do with that in a second. If I can type. Okay, so let's do a little bit of explanation here, because if y equals f of x and x equals a times b plus c, then dy dA equals f prime of x times b, and dy dB equals f prime of x times a, and dy dC just equals f prime of x. So that's easy enough. So that's just single variable calculus. If you did calculus and equals a at b plus c, where c is some vector, then dy dA is f prime of x matrix multiplied by b transpose, and dy dB is a dot transpose a matrix multiplied by f prime of x, and dy dC is actually just let's just call it f prime of x, and then we're going to need to sum it across the batch dimension. But anyway, so this is not obvious, but it's not hard either if you were to sit down and write out, like, what does this multiplication mean in terms of, elements of A, elements of B, and just work out the math. You would find out that this is the case. It's sort of tedious, and we're not going to do it right now. But this is what we're going to do. So, we want to apply this. We have basically the outputs is inputs at W plus B. So think of that as the A inputs, B, W, C, B, which bad names maybe. But anyway, so we're going to do, so we're going to self.grads with respect to W. Let's do B first, actually. So all we need to do here is sum up the grads along the axis equals 0. So basically we have this batch dimension. The outputs are batch size by output size. We really want the gradient to just be output size, so we sum along the batch dimension because they just add up. Self.grads W equals, and again, so you can see that we have, the output is basically inputs matrix multiplied by W. So when we take the derivative with respect to the W, we do inputs transpose at grad. And then finally, we want to return the gradient with respect to the input. So that's the derivative with respect to that, which is just going to be grad at self.params W transpose. Okay, and now we don't have grads defined either, so let's go back and define it up here. Self.grads, again, it's going to be a dictionary where the keys are strings and the outputs are tensors, and that should be pretty good. Let's go here, and I'm actually going to shrink this because it keeps being off the screen, and MyPy seems pretty happy with it, so that is perfect. So, we did the linear layer. We also want to do a tanh layer, but tanh is an activation layer, so let's do activation layers more generally. So what is an activation layer? Class activation is a subclass of layer. An activation layer just applies a function element-wise to its inputs. And so normally this function will be some kind of nonlinear function, but you could do a linear function if you really wanted to. That'd be a little bit strange, but I won't judge you. So what will this constructor take? Well, we want to define some function, and I'll call that cap f for the function type. We'll come back to that in a second. And then we also need its derivative so that when we do backwards with the chain rule, it will work. And I'll just save these. Self.f equals f, self.f prime equals f prime. And now, so what is this f type? Well, this is going to be a function that takes a tensor and returns a tensor. So I can just say f equals callable. Callable is the typing type for functions. And so I give it a list of the inputs and the single output. So f is a callable from tensor to tensor, and that's what this type is. And now I need to import callable from my type hint library. And let's should probably remember to call the superclass constructor as well. And let's run MyPy and see what it does. Perfect. Okay. So now, again, we can create all kinds of activation layers, but today we're going to create one activation layer, and it's going to be the hyperbolic tangent activation layer, which means we need to find an f and an f prime that go into it. So I'm just going to do tan h of x is a tensor, and it returns a tensor. And this is going to be real easy. I'm just going to return the numpy tan h function, except that autocomplete is going to erase it. And we also need a derivative. And I happen to know that the derivative of the tan h function is the following. I say y equals tan h of x, and return 1 minus y squared. That's not obvious, but if you go look at the definition of tan h, if you go work through the math, it works out. And so now I can define tan h, which is a subclass of activation. And its constructor is real simple because it doesn't take any parameters. I'm just going to call the superclass constructor, which is the superclass is activation, and I just want to give it tan h and tan h prime. And one thing I forgot to do was implement the forward and backward for activation, so we should probably do that too. That's an important part of making this thing work. So we have some inputs, which is a tensor, and Hopefully some of you yelled at me about that. So this is real easy. Again, we want to save the inputs because we're going to need them during the backpropagation. And then we just want to return self.f of the input. So in our tanh example, we're just going to save the inputs and return tanh of the inputs. That's real easy. Def backward, self, and we have a gradient, again, with respect to the output. And we want to get a gradient with respect to the input. So again, let's do a little bit of math. If y equals f of x and x equals g of z, then dy dz equals f prime of x times g prime of z. So that's just the chain rule applied element-wise, and so that's what we're going to do here too. So f prime of x is just self dot f prime of self dot inputs, and then multiplied by g prime of z. And here, actually, I've got this backwards, but we're just going to multiply this by the gradient, which is the rest of the derivative. So let me see if I can explain this better, because I think I explained it really poorly. Think of f as being the rest of the neural net, and g being the part being done by this layer. So then g prime of z is actually f prime of the inputs, and f prime of x is the gradient with respect to the outputs of this, which is what we want. So anyway, the moral of the story is that now we have our layers finished, and I think we're pretty much done with layers and with losses. So next is neural nets. So let's make a file called nn.py. nn is for neural nets, and we'll say a neural net is just a collection of layers. It behaves a lot like a layer itself, although we're not going to make it one. Okay, so we're definitely going to need from joelnet.tensor import tensor, and we're definitely going to need from joelnet.layers import layer, and I think that might be all we need for the moment. So we have a class of neural nets, and to initialize it, we are just going to give it some layers, which will be a sequence of layers. Sequence is just, again, a Python typing thing that can be either a list of layers or a tuple of layers. Probably you'd give it a list, but I'll just do sequence in case you want to give it a tuple, and I'll just save the layers. Self.layers equals layers, and that means that I need to go back and from typing import sequence. Anyway, at this point, I hope you appreciate that, the type hints, not just, it's nice, no module named layers. Sorry. Let's run MyPy and see why it's complaining about that. And it's complaining about it for no reason. Okay, good. Sometimes Pylint gets unhappy, so we can't always trust it. Anyway, what I was going to say is that I hope you will agree with me that in addition to having the MyPy checking, these type hints actually make the code a lot more readable, and so you can really understand what's going on much better. So we're going to give the neural net a forward method that looks a lot like our layers forward method, and all we're going to do is for layer in self.layers, inputs equals layer.forward inputs, return inputs. So that's real easy. We're also going to give it a backward method, and so in order to operate a neural net, you just push the inputs through one layer at a time. Obviously, there are some really more complicated neural nets that can't be thought of in terms of stacks of layers, and our library won't handle those, but for the kind of things we're doing, it will handle just fine. So we'll do backwards the same way. We have some sort of gradient with respect to the output of the network. Now we want to go through the layers backwards. So for layer in reversed self.layers, let's say grad equals layer dot backward grad, and then return grad. So we take the gradient and push it backwards one layer at a time until it comes out the front of the network, and then we return it. So that should be good, and let's run MyPy one more time, and it seems to work okay. So that's it for neural nets for now. Okay, so next step is optimizers. Okay, so we have some neural net. We can do a loss function, we can do layers, and now we need some way of, we use an optimizer to adjust the parameters of our network based on the gradients computed during back propagation. Okay, so I always misspell that. Class optimizer. So what does an optimizer do? An optimizer actually has only one method. It's going to be step, and step will take a net, which is a neural net, and it will return nothing actually. And this is the base class again, so we'll raise the not implemented error. So from neural net nn import neural net. And so we're again going to implement only one specific optimizer, and that will be our stochastic gradient descent optimizer. Again, I misspelled it. So our stochastic gradient descent optimizer will take one parameter, which is the learning rate. It's a floating point number, and we'll default it to 0.01, not for any good reason, just because I chose that number. So we'll say self.lr equals lr. And now we need to give it a step method as well. So step, if we have some neural net and we want this optimizer to take an optimization step, how does stochastic gradient descent work? Well, it works pretty easily. For each parameter and gradient in net.params and grads, and here I'm calling a function that doesn't exist, so we're going to need to go write that in a minute. All I want to do is take the param and subtract off the learning rate times the grad. So if I have a function of some tensor, and I compute the gradient of the function with respect to that tensor input, that gradient gives me the direction in which the function increases the fastest. So that means that if I take the parameter and I adjust it in the direction of the opposite of the gradient, that will be the direction in which the function decreases the fastest. And so this, in theory, assuming the function is pretty well behaved, this is going to make the output function and the loss function that we compute the gradient with smaller. And then the learning rate is, a small factor to make sure that our steps aren't too big. So we take derivatives only are for small changes, and so that will work. Okay, but now we need this net.params and grads, which we don't have. So we should write it. So let's go visit neural net again and give it another method, which I'll call params and grads, which takes self. And what does it return? It returns something we can iterate over, so an iterator, and it's going to return pairs of tensors, parameter and gradient. So in typing world, we do that with tuples, iterator, tuple, tensor, tensor. And let me go back up to my typing imports and say, okay, I also need iterator, and I also need tuple. And this will also be pretty easy to write. So for name and param, actually we need to go layer by layer. For layer in self.layers, for name and param in layer.params.items. Let's get the gradient out of layer.grads. So the grad is layer.grads.name. And we want to yield the parameter in grad. So this is really a generator, but I put iterator. That will work too. It's fine. Let's ask MyPy again. And it says, good. So MyPy is happy. That doesn't mean our code works, but it means that it doesn't have any egregious type errors. And I think we're done with that neural net for now. We did optimizers, so now data. Good. So we want to feed our inputs through in batches. And so we need some tools. We'll feed inputs into our network in batches. So here are some tools for iterating over data in batches. since it's not necessarily a natural thing to do. So, from joelnet.tensor, we're definitely going to need a tensor, and we're definitely going to need numpy as np as well. And from typing, we're going to need iterator and named tuple. So if you don't know named tuple is sort of it's a tuple where things are named, and in this capital version they have types as well. And so here's going to be our tools for working with batches. So first let's define batches. Batch is a named tuple, and you have to, there's a new style named tuple format in 3.6 that I haven't used, and someone once asked me why didn't you use that. I said I don't know it. Well, now I know it, but if I use it I'm probably going to screw it up, so I'm not going to use it right now. So I'll have some inputs, which is a tensor, and some targets, which is also a tensor. So now batch has these two fields, and if I have a batch, I can do batch.inputs, I can do batch.targets, and I know they've got to be a tensor and a tensor. So I'm going to define a class data iterator. In an ideal world, I'd probably call it iterator, but there's already something called iterator. You can see it right here, so I don't want to get a name collision. And this is going to have just one method, so call, which means I can call it as if it were a function. And so I will give it some inputs, which will be a tensor, and some targets, which again will be a tensor. And it will return me an iterator over batches. Okay, so and I'm going to raise a not implemented error. And I'm going to implement only one of these as well. I'll call it a batch iterator. I mean, they're all batch iterators, but that's what I'll call it. And I'll give it a constructor because it has a couple parameters. I'm going to give it a batch size, which is an int, and we'll default that to 32. I think that's a good size. And we will also give it a shuffle param, which is a bool, which is true. And that just means, do we want to shuffle the order every time we pass through the data set? And we probably do. And so I just need to save these. Self.batch size equals batch size, and self.shuffle equals shuffle. Okay, so that's easy enough. So what happens when I call this over inputs and targets? In an ideal world, I would shuffle everything together, but I'm a little bit cheating. So what I'm going to do is I'm going to find the start indexes and then just shuffle them. So just these. So I'll shuffle the batches, but not within the batches. So I'll say starts is numpy array range. So we start at 0, we go all the way up to the number of inputs, and then our step size is just self.batch size. So if we leave it at 32, this will be 0, 32, 64, and so on. And then if self.shuffle, then I will just call the numpy.random.shuffle starts. And so now I want an iterator over batches. So I just need to use these starts to create batches. So for start in starts, well, we can find the end. The end is just start plus self.batch size. The batch inputs will just be inputs from start to end. And the batch targets will just be targets from start to end. And I can just yield the batch with batch inputs and batch targets. And I think that's all I need to do for this. Again, we should check it with MyPy and make sure we didn't get anything obviously wrong. MyPy is taking longer and longer. All right, so this looks good, and I think this batch iterator will do what we want. So let's close that and see what's next. Finally, training. Good. So let's add a file called train.py. Okay, so here's a function that can train a neural net. Okay, so here we're going to need a lot of imports. From joelnet.tensor, import tensor. From joelnet.nn, we're definitely going to need a neural net. From joelnet. Let's say loss, I'm definitely going to need a loss function as well as my specific loss. From joelnet.optimizer, I'm definitely going to need the optimizer as well as the stochastic gradient descent optimizer. And from joelnet. Is that all I need? Data, I'm definitely going to need data iterator and batch iterator. Okay, so that's a lot of imports. We need them all, and we're going to find a train function. So what does a train function do? Well, it will take a neural net. That's what we want to train. And then we need some inputs, which will be a tensor. And we need some targets, which will be a tensor. And we need a number of epochs, which will be an int, and I'll say 5,000. That's the number I like. So how many passes over our data set do we want to make when we're training? You know, you could do something more sophisticated like stop training when some metric gets better, but we're just going to do a fixed number of epochs. And then we need an iterator, which is a data iterator. And it will default to the batch iterator with the defaults. We need a loss function, which is a loss function. And by default, it will just be the mean squared error loss, which is actually total squared error. We need an optimizer, which is an optimizer. And by default, we'll just use stochastic gradient descent. And I think that's probably what we need. If we need something else, we'll add it. So what do? Well, we said we're going to train over a certain number of epochs, so we'll just iterate for epoch in range epochs. So we'll compute the loss within each epoch. Epoch loss equals 0.0. And now we want to get batches out of our iterator. So for batch in iterator, and if you recall, the iterator was callable, and you would give it inputs and targets. So we'll go one batch at a time. And what do we want to do? We want to make some predictions. Predicted equals net dot forward batch dot inputs. So we take the inputs out of the batch, we run them forward through our network, and use them to make a prediction. And so then we can use our loss function to compute the loss, and we'll just add it to the epoch loss plus equals loss dot loss of predicted and the batch targets. We can also compute a gradient, which is loss dot gradient of predicted and batch dot targets. And now that gives us what is the derivative of that loss function with respect to every one of our predictions. And we can then propagate that gradient backwards through our network, which will compute the gradient with respect to each of the parameters of the network and then kind of pass it backwards to the previous layer to do that again. And then finally, we have this optimizer, and we want to use the optimizer to take a step on the neural net, which will adjust the weights based on those gradients we just constructed. And then at the end of each epoch, let's print the epoch and the epoch loss. So that is enough to train a neural net. And at this point, our library is done. I mean, batch underscore targets is not defined because it should be batch dot targets. So good. Thank you, MyPy, for catching that. Incompatible default for argument iterator. Default has batch iterator, argument has type data iterator. So that tells me we probably forgot to do the subclassing properly. And indeed we did. So batch iterator should be a data iterator subclass. Let's try it one more time. Perfect. So as I was saying, our neural net is actually, or our library is actually done. And there's a lot of features we could add, and we'll talk about that in a little bit. But for the most part, like, we have everything we need in order to train neural nets. And so the canonical example of something that you can't learn with a simple linear function. Let's write this out. The canonical example of a function that can't be learned with a simple linear model is exclusive OR, because it's just not linearly separable that way. So from ODCnet, from JoulNet dot train imports train, from JoulNet.nn import neural net, from JoulNet dot layers import let's do linear and also tanh, and that might be we're definitely gonna need numpy as well. Import numpy as np. Okay, so for XOR, exclusive OR is if I have 0 and 0, that's not exclusive OR. If I have 0 and 1, that is. If I have 1 and 0, that is. If I have 1 and 1, that's not. So let's define some inputs. It's just going to be a numpy array. And so 0, 0, 1, 0. So there's only 4 possible inputs, so this isn't super exciting. So those are the 4 possible inputs. And now for the targets, again, I'll do numpy array. And the output is either 0 or 1, but I'll represent that as a list of length 2, where 0 is in the first place. So, 0, 0, that's not XOR. 1, 0, that is XOR. 0, 1, that is XOR. And 1, 0, that's not XOR. So that's our data, inputs and targets. And now we define a net. So net is going to be a neural net. And to start with, we said this cannot be learned by a linear layer. So let's show that, or at least show that we can't learn it with a linear layer. So input size is 2 because our inputs all have size 2, and output size is 2 as well. And so, we can train the net with the inputs and the targets. And then real simple for x, y, and zip inputs, targets. Predicted equals net.forward of x. And, normally we should probably do it in a batch, but it turns out that the way we've written this, so far it all works, even if I don't do it in a batch, so I'm cheating. And so we'll just print x predicted y. And so I think, if I now go here and do Python xor.py, you can see that as it runs through these 5,000 epochs, the loss gets down to 0, and it's predicting 0.5 and 0.5, which is not doing a good job at all, and it's because it's a linear layer can't learn this function. So now, the beauty of having a library like this is, let's change our neural net. Okay, after the linear layer, let's add a 10H activation layer, and now let's add another linear layer, and input size here again will be 2, because that's the output size of the previous layer, and we want the final output size to be 2 as well. So now, we actually have a neural net with a hidden layer, only 2 hidden units, but that should be enough for this problem. And we can go back and train it, and you can see that over 5,000 epochs, the loss gets down very small. And, so for 0, 0, it predicts 1 and then almost 0. For 1, 0, it predicts almost 0 and then 1, almost 0 and then 1, 1 and 0. So, if we ran this longer, the loss would get even smaller and the predictions would get even closer to 0 and 1. But anyway, our neural net library has succeeded in solving this XOR problem. And now, this XOR problem is not that exciting a problem, but it worked. So what can we do that's exciting? Well, if you follow my blog, and who doesn't follow my blog, you'll know that I wrote a very good blog post about solving Fizzbuzz using TensorFlow in an interview situation. So here, let's solve Fizzbuzz using our neural net library that we just created. So maybe you didn't read the blog post, maybe you're not familiar with Fizzbuzz. Fizzbuzz is the following problem. This is like sometimes people ask it as like a weed out question for software interviews. Sometimes people joke about it as like, this is the worst question you could ever ask anybody. So for each of the numbers 1 to 100, if the number is divisible by 3, print fizz. If the number is divisible by 5, print buzz. If the number is divisible by 15, print Fizzbuzz. And then otherwise just print the number. Okay, so if you're an accomplished programmer, you can probably think of some easy ways to solve this. I'm just going to copy these imports so I don't have to type them again. And so you might say to yourself, how can I use a neural net to solve this problem? Well, one way is sort of obvious, which is that if you look, there's 4 different classes that you want to predict. There's the fizz class, the buzz class, the fizzbuzz class, and the just the number class. And so from an output side, you can treat it as a 4-class classification problem. So let's write that part first. And I'll call this fizzbuzz encode, and it will take some int, and it will just return a list of ints. So probably from typing import list. And so, if x mod 15 is 0, I'll put it in the 4th class. Otherwise, if x mod 5 is 0, I'll put it in the 3rd class. Otherwise, if x mod 3 is 0, put it in the 2nd class. And finally, if none of those things is true, I'll put it in the first class. Okay, so that's kind of an obvious way to deal with the output. The next question is what to do with the input, right? I mean, we have these numbers 1 to 100. Obviously, if we really want to do a model, we don't want to train on the numbers 1 to 100. So let's train on numbers bigger than 100 and then try and predict on numbers 1 to 100. But we don't want to just have one input. We don't want 2 to be twice as much as 1 and 10 to be 10 times as much as 1 because that doesn't really capture the structure of the problem. So one thing we can do, and it's probably not obvious that it will work, but I tried a lot of things and this is the one that worked, is binary encoding. So if we want to predict on numbers 1 to 100, we'll just train on numbers going all the way up to 1024, which is 2 to the 10th. So we'll just encode 10-digit binary encoding of X. Okay, and if your Python bit shifting arithmetic is not good, you might need to study up because it looks like voodoo. But basically for each I from 0 up to 9, I right shift X by that many bits, bitwise and it with 1, and that will give me the binary encoding. So if you don't understand that, it might be worth studying. Maybe it'll come up on your programming interviews. And so anyway, for my inputs will be the NumPy array. And again, like I said, I want to do this for X in range 101 to 1024. So we're going to train on numbers bigger than 100 so that we can predict on numbers below 100. So the inputs will just be binary encode X for X in range 101 to 1024. And the targets, again, will also be a NumPy array. And that will just be the Fizzbuzz encode X, again, for X in range 101 to 1024. Okay, so that's what we want to learn. And again, we need to determine a net. This will be a neural net, and we got to give it its layers. So we'll start off with a linear layer. Input size is 10 because our binary encoding is size 10, and I happen to know that I want an output size of 50, so 50 hidden units. How do I know that? Because I've done this a bunch of times, and that's a nice trade-off between mostly works and doesn't take forever to train. And so then when I do another linear layer, input size equals 50 because that's what came out of the previous layer, and output size equals 4 because that's the number of classes we're trying to predict, and that's what our targets look like. And so finally, I can train the net, inputs, targets, and let's just do num epochs equals 50 to make sure this works. And finally, for X in range 1 to 101, so this is what we want to do. Predicted equals net.forward on binary encode X. And so that predicted will be, a vector of 4 numbers. And so we want to get a predicted index, which is just going to be the NumPy argmax of those numbers. And again, I'm cheating by not using batches for this. It works, but you shouldn't copy me and do that. The actual index is just the NumPy.argmax of Fizzbuzz encode X. So that's the right answer. And then we need some labels. So labels will be, in the first class, we'll just return the string of X. Otherwise, in the second class is Fizz, third class is Buzz, last class is Fizzbuzz. And let's print X labels predicted index and labels actual index. And so I think that should allow us to evaluate it on 1 to 100. The only thing I did here that was sort of out of the ordinary was only doing 50 epochs because I want to see where it breaks because I'm sure it will break. Python fizzbuzz.py, and sure enough, one, you can see that my predictions are terrible, and two, you can see that if you look at these losses per epoch, it starts off with a huge number, it gets even huger, and then it overflows and becomes not a number. And so because I've done this before and debugged it before, I know that the problem is that the default step size I put in my SGD optimizer of 0.01 is too big. So let's import SGD. And now let's give our trainer a different parameter. Optimizer equals SGD, learning rate equals 0.001. Okay? And I think that will fix it. and you can see it's starting to go slower now. So let's give it the full 5,000 epochs and let it rip. And so what I discovered is that normally these 5,000 epochs don't take that long, but it turns out that when you're running like screen recording software at the same time and it's doing video encoding, using up most of your CPU for that, the 5,000 epochs actually take a really long time. So let's take this opportunity to kind of review what we did and talk about what else we can do to make it a more full-featured deep learning library. So, first step was tensors, and this was cheating. I don't feel too bad about cheating, but if you were building a real deep learning library, you might want to use your own tensor class and make it work on GPUs and do a bunch of stuff like that. For that, we did loss functions. Mean squared error is a good loss function. It works in a lot of places, but if you were doing a lot of multi-class classification, you might want to do cross entropy. You might want to do some other stuff. You might want to add in some kind of regularization term so that you get penalized for having larger weights. These are a bunch of different things you can do with the loss function. Actually, I don't think regularization would fit in this quite entirely well. We'd have to change the API, but that's okay. We can do that. In terms of layers, the linear layer is pretty good as is. You could obviously add a few more activation layers. You could add a sigmoid activation layer. You could add a ReLU activation layer. You could add a leaky ReLU. There's a million different activation layers you can do, and there's a lot of voodoo around how to choose one versus the other, and I'm not good at that. So I chose TANH, and I just stuck with it. It seems to work most of the time. If you wanted to get really fancy, you could start adding, recurrent layers, LSTMs. You could add convolutional layers if you want to start doing vision problems or whatever. You'll probably need to get into that territory. In terms of the optimizers, SGD is a good basic solid optimizer, but you might want to add one that has momentum. You might want to use RMS prop or eta grad or eta delta. There's all these different optimizers of the week, and most of them work better than SGD, but SGD works good enough for us, and it's real simple to implement, as you can see. And then we also had this training piece, and I could have made train be a method on the neural nets. I could have not. It doesn't really matter. What else would I do differently here? Probably not a lot. That's pretty straightforward. So as you can see, this thing has taken absolutely forever to train. It went a lot faster when I wasn't recording and screencasting at the same time, but it's taking a lot longer now. So, why did I do this? Well, I was scheduled to give a talk at a data science conference, and I needed something to talk about, and I thought this would be fun and sort of an exhibition of, live coding madness and skill and things like that. But I also find it interesting to kind of take things apart and see how they work. And the true test, one true test of if you really understand neural networks is, can you sit down and build them starting with nothing? And I don't want to claim that I really understand them, because probably in many senses I don't, but I understand them well enough that I can do this, and that's the sort of thing I enjoy doing. And I'm going to keep rambling here for another couple of minutes as this thing finishes training, where I can sit there and cheer for it. Just imagine that I'm like singing or dancing or something. It will finish real soon. And the sad thing is I could probably run it a lot longer and get better results. Anyway, so for each number, 100 predicted buzz, actual buzz, that's good. These are right, these are right, these are right, these are right, these all look right. Pretty good, pretty good, pretty good, pretty good, pretty good. Oh man. So I don't specify a random seed here, so you never know what's going to happen. But occasionally it gets all of them right. And so if this is one of the times when it gets all of them right, I'd be very excited. Fizz Buzz, Fizz Buzz Buzz. Fizz Buzz. Oh man, 10 left. 8, 7, 6, 5, 4, 3, 2. Look at that. It learns every single one correctly. So that means that our little neural network and our little neural network library are qualified to do any number of programming jobs. So that's great. And I think I have a couple more, one more slide at the end. So thank you for watching. This was fun to do, and I'm super excited that it worked. I will push the code up to GitHub, github.com/joelgrus/joelnet. That's where I'll put it, and you can look at it and download it and run it yourself or try and recreate it or anything. If you want to check out my blog, that's at joelgrus.com. You can read my post on Fizzbuzz and TensorFlow, which makes it seem like I'm much better at TensorFlow than I actually am. Check out my Twitter, that's at Joel Grus. You can check out my podcast, that's adversariallearning.com. And if you're interested in Allen Institute for Artificial Intelligence, check out our website, allenaed.org. We do a lot of really interesting work. There's a lot of really interesting stuff on our website. Depending on when you're watching this, we might be hiring, we might not be hiring, but check out the jobs page if you think it's someplace you might like to work. If you like to do cool stuff, it's a cool place to work. And yeah, this has been fun. Thanks for watching.